Okay, I think we're live.
All right. Yeah, I think it's 9 a.m. Pacific time. So maybe I'll just get started with a couple of logistics. So first of all, it's very nice to have so many attendees here, and let me welcome everyone to the third symposium on advances in approximate Bayesian inference. So again, on behalf of my fellow organizers, let me welcome everyone. Before I introduce today's speaker, let me cover a couple of logistical items, and then we'll take it from there. Okay. All right. So in particular, on the format of this event, as many of you know, AABI has been a workshop or a symposium since 2015. So we started with the first 3 years at NeurIPS, and then in 2018, we actually decided to kind of go one step beyond that and created our own symposium with our own proceedings. So this year it's going to be a little bit different. So instead of having just a one-day workshop, we decided to split up the event into 6 sessions, with today being the first session and the last one being on February 16th. And usually they're on Wednesdays at this time, so most commonly at 9 a.m. Pacific time, but there are exceptions to that. So taking into account that we have speakers from all over the world, and if you want to kind of look it up, you should go to approximateinference.org to find all the details. So the typical format of the event would be one invited talk of 45 minutes, and today's talk is actually a little bit longer because we don't have contributed talks today. But usually for the other events, we also have contributed talks of 15 minutes each. And then there's also time for questions and answers at the end of each talk. So when you joined the event through Zoom, you actually have the option to ask questions on the question and answer channel. You can just type in your questions there. And then in the end of the talk, I'll kind of read these questions for you. And the nice thing is that you can actually also upvote other people's questions, right? So hopefully this will bring up the most relevant and most interesting questions. A couple of other logistics is that you have to register for every event separately unless you kind of watch it on YouTube. So the talks will also be streamed there and will be recorded on YouTube. And also, obviously we had a lot of really interesting submissions, and most of the students and whoever presented posters will not be able to present their talks live. So we highly encourage you to also watch these 5-minute abstracts and reach out to these individual presenters. For more details, please refer to our website, which is approximateinference.org. And before I get to the next step, let me quickly advertise actually already the next session, because in a week from now, we'll have Maya Rudolph from the Bosch Center for Artificial Intelligence speaking. And the title of her talk will be Variational Dynamic Mixtures. We also have 2 contributed talks next week, which is on the Gaussian neural process and empirical evaluation of biased methods for alpha divergence minimization. All right. Having said that, let's get to the next part of the event. And let me stop sharing. Maybe Mike can already start sharing his screen. And let me use the time to actually announce our speaker today. So we're very delighted to have such a distinguished speaker, Michael Jordan from the University of California, Berkeley. So Mike is a professor of computer science and statistics at UC Berkeley, and is probably the most influential researcher in computer science. So he has made several groundbreaking contributions in statistical machine learning, probabilistic graphical models, and also, as of most interest to this community, variational inference. I'm not going to mention like the long list of achievements and distinctions, but just to name a few of them. He's a member of the National Academy of Sciences, the National Academy of Engineering, and the member of the American Academy of Arts and Sciences. And he also received the Ichkai Research Excellent Award and the David E. Rumelhart Prize. So lots of distinctions. So Mike's work has been foundational, in particular in Bayesian machine learning and approximate inference. And so with this introduction, please join me in welcoming Mike. Thank you.
Thank you, Stefan. First of all, let me thank the organizers for not only including me in this event, but also thank you for running the event on behalf of all of us. I think in this year, it's been really important to be able to continue to have these meetings and have a worldwide connection and audience. In fact, I'm currently speaking from Italy, and hopefully the internet will support that that long distance haul for at least some of you. Hopefully some of you are also in Europe as well. All right, so I'm going to give a talk that's a bit unusual in that it's going to be a amalgam of many, many different pieces. It's a story of about a 10-year journey through gradient-based optimization and sampling, and kind of the surprising appearance of continuous time at some point. So just a slide to kind of set this up. I've long been interested in, and will always be interested in, computation statistics bridges. Computation deals with things like modularity and abstractions, but it also deals with time, temporal issues. How long does it take for something to run? Statistics has dealt with a fairly complementary set of issues having to do with uncertainty and decision-making under uncertainty. It's not been so good about talking about time, about how long things take. Most of the research on temporal issues was asymptotic for years. It became more non-asymptotic and started to become a little bit more computational only recently. I would say in the Bayesian world, it's still not so much of a focus. We talk about how long things take, but they're asymptotic results. And we talk about efficient algorithms like Gibbs sampling, where we really don't mean efficient. It may be efficient, but it may not be, and it may take an indeterminate amount of time. So we need to talk about trade-offs between inference and computation. And we need to do that as a function of data set size and a function of all kinds of other variables. And we're kind of only getting going on that topic, really. So I'm going to be talking a lot about optimization today. Optimization is more useful on the frequentist side of statistics, but it's going to then play into sampling, and then we're going to emphasize the ties between optimization and sampling. And it is arguably the case that a frequentist analysis is a little easier here, because you can talk about optimizing things, and you can talk about various criteria, and you can talk about non-asymptotic. So kind of the challenge for many of you, perhaps in the audience, is to take ideas like this, these computational machines of dynamical systems and optimization and sampling, and bring them more thoroughly into the Bayesian world and vice versa. All right, so the second bullet here kind of is the main point I want to make on this slide, is that the algorithmic focus has been gradient-based methods. I think you all kind of know why. It's not impossible to compute gradients. It's efficient. Often stochastic gradients are quite efficient to compute, and they're successful in practice. And we've been building theory to explain why they're successful in practice. There's also a notion of acceleration, which, as its name suggests, allows you to talk about going faster, but it also allows you to talk about things like lower bounds. How fast can you possibly go? And if you start talking about lower bounds, you start to strip away the details of specific algorithms and points of view. And if you think about lower bounds in statistics and lower bounds in computation, putting those together feels like a very promising way to think about doing research. And in fact, that's one of the things that I've been doing now for several years, and I'll be talking about that today. So I'm going to warm up with a project that kind of got us started on some of these issues: high-dimensional optimization in the non-convex setting. This was work with Chi-Jan and several other colleagues. We've had now several papers on it, and there's a kind of a summary paper that'll appear in ACM later this year. So this is about optimization in the context of interesting geometry, in particular where there are saddle points. And saddle points are important in high dimensions. There's going to be lots of them, probably way more saddle points than there are local minima, something of an interesting fact. And they can be very hard to get out of. You can arrive at one and sort of stay there for a long, long time. You'll have your learning curve flatten out. It's evidence that you're often in a saddle point, and then later you'll come down again. And if you're trying to think about a theory of computation and how fast things occur and can you be in real time, staying in a saddle point for an arbitrary amount of time, especially in high dimensions, kind of kills any possibility of such a theory. So we have to talk about how fast can you escape from saddle points and make a theory out of that. So let's just start by talking a little bit about classical analysis, but now non-asymptotic. We'll do it in the convex case. All right, so let's consider the problem of minimizing a convex function. Details in this talk are not going to matter too much. I have them on the slides. I have lots of equations, and I don't want to spend a lot of time on details. The overall story is the kind of point of the talk. I have the details, though, for those of you who are experts. So as you probably know, in convex optimization, gradient-based methods are not only good, but they're optimal. They'll converge to a global minimum. And surprisingly, perhaps, the number of iterations to arrive at the minimum is independent of the dimension-free. So you can run gradient descent in infinite dimensions on a convex problem, and it takes just as many steps as it would in finite dimensions. And that's kind of already a hint of why gradient methods are so successful. I wish I could get rid of the thing at the top. I guess Zoom has done that. Stefan, are you seeing my titles at the top or not? I'm not hearing you, so.
Yeah,
sorry.
we can see it fine.
Yeah, we can see it, yeah.
Okay, so you're not seeing that. Okay, good. So anyway, here's kind of the classical setup due to people like Nesterov and others in the optimization literature. You have a gradient Lipschitz or smooth function, and a first order stationary point is where the gradient nearly vanishes. And Nesterov proved that the number of iterations to arrive at a first order stationary point for these convex problems is 1 over epsilon squared. So epsilon is how accurate you are, and if you want to be really accurate, it'll take you more iterations. The beauty of this result is that it's not asymptotic. It is exactly the number of steps that it'll take. It's an upper bound on that. There's a Lipschitz constant and the number 2 and the initial distance to the optimum. There's no other free constants, and it's a really meaningful result. So if you get results like this, you're kind of done. You've kind of nailed how fast this algorithm takes in a particular class of problems. So now the question is, what happens if we try to do things like that in the non-convex world? Is it just kind of get really, really complicated? What can you say? And the answer, the fact is going to be, we're going to be able to say a lot. So if you run gradient descent on a surface like this, you probably know you may hit a local minimum, you may hit a local maximum, and most problematically, you may hit a saddle point for a long time until you eventually escape. Okay, so we've analyzed this situation, and I'm not getting into details. This paper is on the web, but here's a theorem which says that under a little bit more of a smoothness condition, we now have smoothness for the Hessian, not just for the gradient. A particular algorithm that's a perturbed form of gradient descent. There are many algorithms that we've analyzed. This is a particular result for one of them. They all have the same rate. A particular form of perturbed or stochastic gradient descent, if you will converge in a rate which is 1 over epsilon squared. Okay. Now, what does it mean to converge here? It means to arrive at a second order stationary point. And so that rules out the saddle points. Those are not second order stationary. So second order stationary, kind of the bowl-shaped stationary points where you have no negative eigenvalues. So it rules out saddle points. So if you start on one of these surfaces, you will get yourself past the saddle points and arrive at some other kind of object, a local minimum, in time, which goes as 1 over epsilon squared. So it's just as fast as gradient descent. All right, and again, no free constants there. Now there is a tilde there, which is where we typically hide dimension dependence because we're not able to figure it out. In this case, we were able to figure it out, and the dimension dependence is logarithmic to the 4th power in D. D is the dimension of the ambient space. Okay, so I don't believe in that 4. I'm going to tell you about the proof technique in a minute, and I believe it's probably logarithm, but we haven't been able to get rid of that 4 now for several years, so it's an interesting open problem. If you then write down gradient descent in the convex case next to perturbed gradient descent in the non-convex case, you see the results are very much parallel. The rates are essentially the same, but we're able to bypass the saddle points. I want to say something about the proof technique here because that kind of ties into the theme of the rest of my talk. It's going to turn out to be probability theory, very surprisingly. The question is really a geometric question, differential geometric question. Around a saddle point, there is a region, this green region here, where the flow is mostly towards the saddle point. Okay, and outside of that green region, the flow is mostly away because you'll have a negative eigenvalue and you'll flow away. In fact, exponentially fast. So the question, the analytic question, is to figure out how thick that green region is. And the problem is that the green region is not just a slab, it varies smoothly because the Hessian is not constant in this region. So you have to do some sense of serious differential geometry to figure out that thickness. We figured that out instead by using probability theory. And the key idea is a coupling story. you start two coupled diffusions, Brownian motion-based diffusion, at a distance r apart. If r is really small, both of these diffusions start in the green region, and their flow is mostly towards each other because they're flowing both towards the saddle point. Therefore, they will couple with high probability relatively quickly. If r is a little bit bigger, one of them will see the negative eigenvalue and it'll start to fly away, and it will never couple to the other diffusion. And so if you calculate the coupling time, there's going to be a phase transition in coupling time. And if you can bound that, and that's what we're able to do, you can get an estimate of the thickness of that green region. And that is the analysis that gives you this logarithmic to the fourth power of d analysis. So many analyses, as I alluded to, of convergence of algorithms are asymptotic. This is not asymptotic, but moreover, most analyses don't have the dimension dependence figured out. And for us, it was critical to get the dimension dependence, because that's kind of the whole point, is that our algorithms are often in very high dimensions. And if they run aground in high dimensions, then they're not very good. Okay, so I would argue that that's kind of a really clean result. And when you have a clean result like that, you wonder, are you done? And so you start to now ask about lower bounds. Are we going as fast as we can possibly go in this class of problems? And so we're going to talk about this notion of lower bounds. Optimization theory has had a lot of lower bounds. The Russian school, Nemirovsky, Yudin, Nesterov, and others have worked out lower bounds. We're going to argue that to really understand these lower bounds, it's important to go to continuous time, that the notion of going as fast as you can go is really a geometric question, and it's best revealed in continuous time. The earlier work by the Russian school was in discrete time, and it was kind of a mystery of where the bounds were coming from and how to interpret them. So this work is very much continuous time dynamical systems oriented. Variational and Hamiltonian ideas are essential to pull this forward. And then symplectic ideas arose to the sampling perspective, as we'll talk about later. So Andrew Webstone and Aisha Wilson did the lion's share of the work here. They were students of mine at Berkeley, now at Yale and MIT. And then Michael Betancourt also contributed. So just kind of a philosophical comment that differentiation and integration are kind of, two sides of the same coin. There's something called the fundamental theorem of calculus that relates them. And mature mathematical fields do a lot of differentiation and a lot of integration and go back and forth between them. And so physics certainly does. Statistics does as well. And the numerical disciplines like finite element analysis and Monte Carlo do a fair amount of both differentiation and integration. I would argue that optimization in this sense, maybe surprisingly, is not so mature. It's really based solely on differentiation. You'll see very few integrals in optimization papers. All right, so let's try to bring some integrals into optimization. All right, so that's what we're going to do here. We're going to be working in the unconstrained setting. And let's start with convex optimization. Will definitely not be convex after a while. Also, I've been working very recently on constrained methods in this kind of variational spirit that I probably won't have time to talk about, but that's an active area. So here's classical gradient descent written slightly differently. We're also going to now talk about its convergence rate in terms of the number of iterations rather than the epsilon we were using before. So that's the formalism we'll use for the rest of the talk. So after k steps of gradient descent, you will be within a ball of size 1 over k of the optimum. So that's a classical result, really due to Nesterov and others. It's not that old. And the question became at some point, is it optimal? Is this the best you can do on a convex smooth function with a gradient-based method? And a complexity theory kind of emerged in optimization theory with Nemirovsky and Yudin writing a famous book about it. And they were able to show that there's a lower bound that's faster than gradient descent, that it's 1 over k squared instead of 1 over k. And so there was then an open problem for a while about, is there some algorithm that goes faster than gradient descent, but only uses gradients? And maybe at first it felt like that was not possible because gradient descent is steepest descent. So how can you go faster? And it turned out there was an algorithm that goes faster. There was several algorithms. Here's the famous Nesterov algorithm at the bottom of the page. It's a two-part algorithm. It's a second order difference equation, and it has a rate of 1 over k squared. So it beats gradient descent, but it's only based on gradients. And so again, details aren't mattering so much here, but basically it uses the last two gradients and builds up a little bit of momentum, if you will. So there's lots of kind of analogies and metaphors being used to understand this. And there's a kind of raft of algebra you can do, but there's not been a lot of really, I think, intuitive understanding and kind of physical understanding of this. So we've argued, and others have argued as well, that you need to go into continuous time to actually understand this phenomenon. So let's go into continuous time. So if we just start with gradient descent, if you take the step size to 0, you get gradient flow. And it is also, by the way, the case that if you look at gradient flow from the convergence point of view, on a convex function, it has a rate which is 1 over t. And so that corresponds to 1 over k in discrete time. Moreover, if you discretize this differential equation, you will get gradient descent. So that's all very classical. There was an important paper by Wei-Jie Su and colleagues in 2014 showing that if you take the step size to 0 for the Nesterov algorithm, you will in fact get a second order ODE. Not surprising, there are two equations there. And the form of it is interesting. It's second order, and it's got a damping term, which is 3 over t. So, it's a mysterious 3 sitting there, and 1 over t is the right damping. You can analyze this and see that the convergence rate is 1 over t squared, which corresponds to the 1 over k squared of an accelerated algorithm. And so we came in at this point and asked, why this differential equation? Where is this coming from? What's special about this? And so you can kind of think of this like, Lagrange looking at the equations of physics, F equals ma, and saying, well, those are interesting ODEs, but where are they coming from? Is there an underlying principle that derives equations like this? And so we went after a Lagrangian or variational approach to this kind of accelerated phenomenon in optimization. All right, and so that's what we managed to find. We found an object we call the Bregman Lagrangian. And again, I'm not interested in the details here for this talk, but just to say it's got these alpha, betas, and gammas. Those are just functions of time that are degrees of freedom that give you a space of algorithms and not just a single algorithm. So they're just diffeomorphisms, and they're not the important part of this. The important part is the Bregman divergence d sub h there, which measures the divergence between x, where you currently are, and x plus a time-shifted x dot. So it's kind of an elasticity in the direction of motion. The other important part is the red part there, which is the function you're trying to optimize. So you can think about the Bregman divergence as a kinetic energy, and you can think about the function you're trying to optimize, f, as a potential that you're trying to go down. Okay, and so here's a little picture showing a Bregman divergence if you haven't seen that before. All right, if you let the Bregman divergence be based on the quadratic function, the h function that measures distance is quadratic, then you'll get Euclidean distance, but moreover, that Bregman divergence becomes 1/2 x dot squared. So it literally becomes a kinetic energy. And so this is literally a time-varying Lagrangian, okay? So what do you do with Lagrangians? You put them inside of calculus of variations, and you say, let's minimize over the Lagrangian from some time, starting time to some ending time. Mathematically, that is characterized by the Euler-Lagrange equation, which is simply a differential equation that arises out of plugging in that Lagrangian at the top of the page to the the set of partial derivatives and total time derivative here at the bottom of the page. So when you do that, it's just a 3-line exercise. You will get out this differential equation at the bottom of the page. This is an equation which minimizes our Bregman Lagrangian. Our Bregman Lagrangian is time varying, and so not surprisingly, this differential equation at the bottom has a time varying damping term. It's second order, so it likes to oscillate. And it has a really complicated third term there, which is really geometric. It has the h function, which measures distance in it. It's kind of got some geometry coming from that term. If you plug in for alpha of t, logarithm t, and you set h to be the quadratic, this whole thing reduces to the Boyd and Candace equation. That 3 comes out automatically, 3 over t comes out automatically from this equation. But not only that, a whole range of other accelerated methods come out from this equation. And in fact, sort of most accelerated methods come out from this equation. All right, so that's already kind of interesting, but this equation, this Lagrangian, has a lot of mathematical properties which help you to understand why these algorithms are accelerated. All right, so in particular, if you pick different desired convergence rates, alpha of t, you set alpha of t to be logarithm of t, you get gradient flow. If you set alpha of t to be logarithm of t squared, you will get out the Nesterov acceleration in continuous time. But you can set out alpha to be other rates, and you can get out other algorithms or other continuous time algorithms with different rates. Now, the interesting fact is that every one of those algorithms will follow the same path in phase space. So if you look at that little plot up there, there's a line in phase space, and all of the algorithms will follow the same path. All right, so the geometry is actually, we've kind of revealed that the geometry characterizing accelerated methods is constant. There is a characteristic geometry, and all that's happening in acceleration, the rates differ because you move along that same path at different speeds. All right, so in continuous time, you actually can go at any speed you want to, because you can just change your clock, your definition of time, and zip along that curve at any rate you want. So that seems almost troublesome, because the phenomenon of acceleration of having a lower bound seems to have disappeared. All right, and here's where it became interesting. Let me just skip this slide. This is a Lyapunov function argument showing we can get the rate once and for all. So the comments I was making there about rates comes out from a Lyapunov story, but let me skip that. All right, but here were the mysteries then, is that this acceleration phenomenon seemed to have disappeared. But it didn't disappear. What happens is that if you want to now discretize the differential equation, you will come back into discrete time and put it on a computer. It'll turn out that the fast differential equations that are going faster than the lower bound of Nemirovsky, you are not going to be able to discretize those equations stably. Okay, it's going to be impossible to discretize them stably. Right? Somehow you're going around the curvature too fast and you can't be stable. All right, so the acceleration phenomenon geometrically is in part a stability phenomenon about how fast is it possible to go. All right, so I'm going to tell you a little bit more about why I'm saying this, and we also then have to worry about how do we discretize once we know it's possible. All right, so for example, for the class problems I was showing earlier, these convex smooth problems, the theory will tell you can't discretize once you go faster than 1 over t squared. So even though in continuous time you can go at an exponential rate, if you try to discretize that differential equation, you will fail. Okay, and so symplectic integration came into our story at this point. I had learned about this when I was a young professor taking classes and filling out my education. And it's a beautiful topic if you don't know about it. Let me just briefly say kind of what it is. It came from Hamilton and Jacobi and other leading lights at the end of the 1800s, 19th century. And they were concerned with discretizing discrete differential equations obtained from physical principles like Maxwell's equations or F equals ma. And they knew that those equations in continuous time conserved various quantities like energy, momentum, and general volumes of phase space. And they asked, is it possible to discretize in a way that still conserves volumes and phase space? And you might think that's maybe possible because volumes are like determinants, and determinants are polynomials, and you could put a polynomial constraint that a certain polynomial will be conserved as you transform from discrete to discrete time. So anyway, they worked out they figured out you can do it, and they worked out algorithms that actually do it. And these are called symplectic integrators. The leapfrog method that's used in MCMC is actually an example of a leapfrog of a symplectic integrator. All right, now why is this relevant? This perspective says that the right way to think about a dynamical system is not to put a arrow at every point of a trajectory. Don't think just about a vector field, but think about a triple of vectors at each point, and that defines a little volume element. And as that volume element flows along the flow of the differential equation, the volume element can shear in various ways, but it should stay constant in volume. All right, so that gives you a little control around the tube of the trajectory. And it turns out that these methods are much more stable And you can take much larger step sizes when you discretize than with other discretization methods. And so these are widely used. It's a 100-year-old field in physics and chemistry, especially for large-scale problems, because you can take so much bigger step sizes. And that is the connection to acceleration, okay? It's because you can allow now to take very big step sizes and start to kind of get towards accelerated methods. Just to show you this was true, we had done some simulations early on. This is symplectic integration of our Bregman Lagrangian. We now turn it into a Bregman Hamiltonian with a Legendre transform. And you can see the rate is going down. It's oscillating because it's building up momentum. It goes up and down. This is on a particular high-dimensional quadratic. Here's another example where we compare directly to Nesterov and a different problem. So it actually is asymptotically getting faster over time. And it's as good as Nesterov, but actually it turns out it's faster than Nesterov. If you turn up the step size, if I go back and forth between them, there's the step size for the small step size. If you have a bigger step size, the symplectic method stays stable and continues to converge, and Nesterov goes unstable. Okay, so this was kind of empirical. What can we say theoretically? So I'm going to turn to that in a moment. And talk about some, further symplectic geometry ideas. But before I do that, just a little brief interlude, which is the machinery we've built. We've done two things in the talk so far. We have machinery for talking about continuous time and Lagrangians, Hamiltonians generating differential equations, a machinery for then making algorithms out of that, and reasons to believe these are good algorithms. They're fast, they're gradient-based, and so on. We also have got ways to analyze saddle points, so we can do non-convex sorts of things in discrete time. So can you put these two ideas together? Can you now use our new continuous time theory and talk about non-convex problems? And yes, you can. Just very briefly, I work with Chi-Jin and Praneeth Netropali. And I just want to mention, I'm not going to get into this slide in any detail, but the Hamiltonian or Lagrangian perspective I showed you on previous slides led to an algorithm, and then a Lyapunov argument then turned it into an analysis. Here we are directly using our Hamiltonian to help structure the analysis. This is a more complicated problem with these saddle points and all. So it's a complicated analysis. And we look at the Hamiltonian and it has several terms to it, and we analyze separately those terms and are able to put it all together. So it's actually the Hamiltonian that not only guides the design of the algorithm, which is a simple algorithm, so it doesn't really guide much there, but it is critically the Hamiltonian that guides the theoretical analysis and allows us to give these tight dimension-dependent bounds. All right, so let me just show you the result here. Again, not getting into details, but at the top of the slide there, you see that we were able to show that, that this perturbed gradient descent converges to second-order stationary points. In other words, it misses all the saddle points at a rate which is 1 over epsilon to the 7/4. That's faster than 1 over epsilon squared. So this proves that accelerated methods actually avoid saddle points more quickly than non-accelerated methods. So in other words, they work also in the non-convex domain, not just the convex domain. Okay, so let me now spend a little time on this connection to to symplectic integration. This is a whole paper of its own that we published earlier this year. And I'm going to just kind of skip through and give you some high points here. But the work with Guillermo Franca and René Vidal. There's been kind of a disconnect in my talk so far, which is we've been using these physics ideas like Hamiltonian and Lagrangian systems. Hamiltonian systems in particular are not generally thought of as dissipative. They are systems that allow you to describe oscillations and things that conserve energy. And in optimization, we're not trying to conserve energy. We're trying to get rid of energy and go down and converge to a point and stop. All right, so why should there be a connection to Hamiltonian systems? And same kind of thing in Monte Carlo methods, they should converge to a distribution. They don't stop, but they jitter around at some point. Why should Hamiltonians be relevant? Well, you already have a hint because there exists something called Hamiltonian Monte Carlo or hybrid Monte Carlo that there should be a connection. So we're going to try to deepen this connection. And what we're going to do is define a class of dissipative Hamiltonian systems. All right. And we're going to use that to analyze optimization methods. All right. So again, I'm not going to get into details on these slides. It's a whole separate talk, but I just want to give us a few high points. Okay, so as I've alluded to, conservative Hamiltonian systems are ubiquitous, but we don't want conservation. We want dissipation. So can we do that with kind of variational or Hamiltonian machinery? And we are going to want to do that. And the key is going to be, we still want to use symplectic ideas, because symplectic ideas guide us into how to discretize, and they give us, say, algorithms and analyses. Moreover, what this paper did, which was new, is it was able to do backward error analysis of the discretization, and actually therefore prove that the discrete algorithm was as fast in discrete time as the underlying continuous time. So we really now have tied the whole theory together using symplectic ideas. All right, so we're going to need to get into Hamiltonians to do this. This here is just a little hint of the kind of error analysis that you can do in the field of symplectic integration. So this is developed by, there's many names there at the bottom of the slide, people who do numerical analysis. There's a Fields Medal given for some of this and so on. And the way it's done is that you looked at perturbed dynamical systems and think of the discretization as having the exact flow of a perturbed system. Okay, so it's not that you're trying to look at errors per se. You're saying something is exact, but you've perturbed your Hamiltonian. Okay, so that's kind of the rough idea here. And in particular, you can get exponential convergence rates in the errors by doing this sort of a perturbed flow approach. Okay, a whole field of its own. All right, now you can do this in particular if you can find a Hamiltonian, the perturbed Hamiltonian. And the way you do that is you look at the original structure in your Hamiltonian continuous time, and you say, I want to preserve that structure as I go to discrete time. All right, so now the structures you talk about are geometric ones. So we have to talk about a little bit of manifolds. And in fact, now the underlying mathematics starts to become more clear. Hamiltonians are defined on manifolds most naturally, okay? There's a one-to-one connection between manifolds and Hamiltonians. And symplectic geometry is defined in terms of exterior forms on manifolds. So this is kind of the right place to talk about this whole field, all right? And in fact, if you talk about manifolds, you can talk about their tangent spaces, their tangent bundles. And there's a theorem that says that tangent bundles are symplectic manifolds. They have these exterior forms on them. And the theorem at the bottom of the page is the most important one, that a dynamical system preserves symplectic structure. These volume elements, if you will, these exterior forms are conserved if and only if you have conservative Hamiltonian dynamics. All right, so this is all kind of a 100-year-old topic. And moreover, if you bring one more ingredient into the notion of a time derivative on these manifolds, in other words, the Lie derivative, you can talk also about energy conservation. Okay, so now when you talk about the numerical integration part of the story, there is a recipe that allows you to construct integrators which exactly conserve these volume forms on your underlying manifold. And so the mathematics kind of tells you how to do all of this, and it became entirely standard in a lot of applied fields. The backward error analysis idea then allows you to actually bound the error as you go from continuous to discrete time. All right, so at red in the bottom here, I've alluded to the problem here. This is all great, but what's the relevance to our dissipative systems? Okay, and in particular, we've lost the Hamiltonian being conserved. We're not going to conserve energy for dissipating things. All right, so what are we going to be able to do here? All right, and so here's what we've done. There's a generalization of symplectic manifolds called a presymplectic manifold. And I'm going to show you a picture here in a minute, which will convey the basic idea. It takes the original manifold where you're wanting to dissipate and embeds it in a manifold of one higher dimension. On that manifold, you have a conservation law and you have a Hamiltonian and everything. And then all we have to do is to go from the higher dimensional manifold back down to the lower dimensional manifold with a gauge function, all right? So here's a kind of a picture that we have all the beautiful mathematics we were talking about on this bigger manifold, and the blue manifold where our dynamical system is actually defined is obtained by a gauge fixing, a reduction, a dimension reduction from the high dimensional surface to the lower dimension one. All right, so I'm about ready to finish on this. This is all I wanted to show some of you, all the machinery that goes here. So you can now define a presymplectic integrator for a dissipative Hamiltonian system. And it's just mathematically, it is that you define a symplectic integrator on the bigger manifold, and you do the gauge fixing to turn that thing into a integrator on the embedded manifold. So we can use all the machinery, we can do backward error analysis, and we can say that whatever rate we had at continuous time under this Hamiltonian is preserved when we move into discrete time. Moreover, we get algorithms that turn us from from continuous time into discrete time. Okay. And so here's a statement of that kind of theory. If our Hamiltonian has this kind of kinetic energy form plus a potential form, then we have a theorem here which shows that you get the conservation of the rate, up to a tiny exponentially small error. The Bregman Hamiltonian, which is the Hamiltonian version of the Bregman Lagrangian I told you about earlier, is an example, a special case of this general framework, where you have the Bregman divergence. We have the dual here because we're working with the Hamiltonian, and you have the potential function. And so that differential equation I showed you earlier is in continuous time. We can now prove that that's conserved, its rates are conserved when we go into discrete time. This is one slide that shows actually executing this, going all the way down to the numerical integrator. This is what you would put on the computer to actually integrate the system and get the kind of curves I showed you earlier. So it's really become a completely standard, if you will, set of mathematics that allows us to actually design dynamical systems that converge at desired rates and, in fact, optimal rates for a wide class of optimization and inference problems. Okay, so that's what I wanted to say about that. And that's kind of the main bulk of the talk. The rest of it is going to be a little bit of dessert, a couple of more further applications of this set of ideas and the style of thinking. Again, what have we done so far? We've identified ways to approach non-convex problems using coupling arguments, basically. We've found ways to analyze dynamical systems in continuous time and turn those into rates of convergence and optimal rates. We're going to now try to apply this more directly to Markov chain Monte Carlo ideas. And we're going to try to apply this to other kind of problems, for example, saddle point problems in game theory, which is, to my mind, a very important future direction for Bayesian inference, for sure. It's already been, Bayesian ideas have been in game theory a lot, and frequentist inference as well. All right, so let me just mention briefly a project with student Eric Mazumdar, where we're going to be looking at the same kind of methods we've been talking about, gradient-based optimization and sampling kind of, or Lagrangian kind of algorithms applied to game theory. So we're trying to find equilibria, for example, Nash equilibria, which are saddle points where one agent is happy to go down and the other agent is happy to go up in the other direction. That's a saddle point. And in game theory, you're not trying to avoid the saddle points, you're trying to converge to the saddle points. So we kind of have a counterpart to the problems we've been looking at so far. All right, so again, kind of briefly, just going through no details, a zero-sum game, has got this function that, hopefully has a saddle point, and we would like to find those saddle points. Those are the Nash equilibria. This slide is too busy, but just to say that if you just naively apply gradient descent ascent to these problems, these game theory problems, where you're going downhill in one direction and then uphill in the other direction, that will not converge. It may converge to limit cycles, or it may just not converge at all. All right. So people have been working on that. There's many other proposals trying to avoid the limit cycles and converge and so on and so forth. And you can sort of see the problem here on this slide. On the left there, you see some pictures of a dynamical system. The F function is given by the level curves there. The green crosses are Nash equilibria. They're saddle points which you would like to converge to because one agent is going up and the other is just going down. They're axis parallel saddle points, if you will. The blue star in the middle is a saddle point, but it's tilted. It's not a Nash equilibrium. But these gradient methods have no idea that it's not a good point. They look at it and they see, well, it's a saddle point. I should converge to it. So they do. So that has been an open problem, is how do I get gradient methods to avoid the non-Nash equilibria? And there's going to be lots of them in real problems. And people didn't really realize this, I think, until they started to realize some of the algorithms being used were not working, including things for like GANs and neural nets. All right, here is our new algorithm. We call it local symplectic surgery. So that symplectic word is now coming back again. Here, the symplectic component of the vector field is actually the bad part of the vector field. This is the part that causes the oscillations, it turns out, the limit cycles. If we cancel the symplectic part of the vector field, we get rid of those problems. And so this algorithm, which I won't get into details here, but it's this little two-part algorithm that effectively cancels the symplectic part of the vector field, and therefore it will converge to Nash equilibria, and only to Nash equilibria. It will not converge to a tilted saddle point. So you can see that on the right there, the red dashed lines are converging to the green crosses. That's good. But the red dashed line will not converge to the star in the middle because it goes near it and it sort of sniffs out that this is actually a saddle point, and it flows away from that. All right, so I wanted to bring this up just to sort of show you that, and this is a very active topic, many people are working on it, that the geometric and symplectic ideas are actually directly relevant to not just avoiding saddle points, but also to converging to saddle points if that's your desire. Okay, so the last part of the talk will be just a little bit on parallel work on Markov chain Monte Carlo, or more general stochastic processes. I have a whole bunch of papers on that you can consult here. Let me just briefly overview some of our results. So first of all, why is this being put together in this same talk? Well, because we're using exactly the same kinds of mathematical machinery. We're using coupling arguments, we're using dynamical systems, and we're going to continuous time. And so the ideas really flow back and forth between Markov chain Monte Carlo and optimization using these kind of mathematical tools. All right, so one example was a paper where we showed that Langevin diffusions can actually be accelerated. That was not known that it was possible. This is work with Shang Cheng. We also, in fact, took that even further and showed that a particular form of Langevin diffusion, an underdamped form, is actually Nesterov acceleration on a simplex of probability measure. So that the tie becomes very, very strong there. That's with Yan Ma. We also were able to look at higher order Langevin diffusion and find that we got other forms of accelerated MCMC algorithms here. Essentially, the higher order diffusions are smoothing the Brownian motion, and they can go faster and faster. Also, the one I will talk briefly about is that Langevin algorithms can go fast enough now with these kind of machinery that you can actually use them in the context of Thomson sampling, which is Bayesian multi-arm bandits, and achieve logarithmic regret. The best known results in frequentist analysis have logarithmic regret. And so that's kind of a real computational story there, that Langevin non-asymptotically can go fast enough that you can actually find the optimal action in Thomson sampling, Bayesian bandits, quickly enough that you can converge with logarithmic regret. Lastly, maybe somewhat surprisingly, you don't need smoothness for Langevin diffusion. This is work with Niladri Chatterjee and others. So let me just briefly mention this overdamped story. It's been kind of our driving machine here. It's a second order differential equation. Okay, so first of all, this is the overdamped case is the classical one. We're going to talk about underdamped briefly here. So here's overdamped Langevin diffusion, right? It's just a stochastic differential equation where you have Brownian motion as your driving stochastic noise, and you have a gradient. Delta U is your gradient here. All right, and it can be discretized, and it has the right stationary distribution, and so on. And in recent line of work, mostly done by people in Paris, Dalalian, Dermus, and Moulin, convergence rates, non-asymptotic convergence rates were found for these algorithms. And so basically they are 1 over epsilon squared. If the number of steps n is bigger than 1 over epsilon squared, then you're within an epsilon ball of the optimal probability distribution. And that's been improved a bit. But anyway, d over epsilon squared is kind of the rate that has been achieved. So we thought about trying to do this with a second order algorithm, not overdamped Langevin, but we're going to use now an underdamped form of Langevin, where you oscillate because you put a velocity term together with a position term. So now it's a second order SDE, and the Brownian motion is in the velocity, not in the position. So it's much less of a jittery path than with the overdamped Langevin, okay? And so this has the right stationary distribution and so on and so forth. We can discretize and get a second order MCMC algorithm, but now can you do the theoretical analysis? And it turns out you can. Again, we use this coupling kind of story that I talked about earlier, and we were able to show that the convergence rate of this algorithm is actually 1 over epsilon, so much faster than 1 over epsilon squared. And its dimension dependence is actually square root of d and not d. It's not independent of dimension like in the gradient descent case, but somewhat surprising. You would think that you'd have to pay a cost which is linear in d, because Brownian motion sort of sees all the dimensions. It doesn't know. It's a random walk, right? But it turns out that it's square root of d is possible with Brownian motion. Okay, and let me skip over that slide. And here again is the proof technique, as it turns out to be a form of reflection coupling. All right, last little thing I'll spend just a couple minutes on. Again, this is really dessert, and then I'll try to finish up. Is just I want to briefly allude to this story. This is a very new paper. Eric, again, Mazumdar has led this with Aldo Pacchiano, and there's Jan Ma and Peter Barta, my colleague at Berkeley. So we've been working on Langevin MCMC algorithms in the context of banded algorithms. Okay, so banded algorithms, hopefully you all know, are kind of decision-oriented learning systems. Each arm has an unknown reward distribution, and you pick the arms stochastically or in some way, and you get the reward, and you try to converge the arm that has the highest mean reward. Okay. There is a Bayesian approach to this, and there's a frequentist approach. The frequentist approach has been the most analyzed. There's the famous UCB algorithm, which adds a penalty to the mean reward, and has a regret bound, which is logarithmic, and most of the theory has been done for that. The Bayesian approach here is Thomson sampling. It's older, but it's been less analyzed. As typical of the case, the Bayesian methods are harder to analyze. Basically, it forms a posterior for each of the arms, and then it samples from those posteriors and picks the arm that has got the highest value of the sampled posterior. All right, so it's not well understood, Thompson sampling, because it's hard to analyze outside of conjugate families. The only analysis I'm aware of has been done with conjugate families. And if you are outside of conjugate families, not only cannot analyze it, but the algorithm will probably be a slowly converging MCMC algorithm, and it will converge too slowly to have any hope of logarithmic regret. All right, so we have gone at this problem and made a lot of progress. So we have new concentration rates of the kind that we usually get in frequentist methods, but these are Bayesian. So these are posterior contraction rates that are fast enough so that we can get these logarithmic regrets. And so we put that then in the context of a Langevin MCMC algorithm as our machinery for updating the posterior for Thompson sampling. All right, and so again, I'm not going to be able to get into details here, but let me just flash some slides that you could look into if you want. Here is our new concentration inequality. As you can see, it's a Bayesian concentration. It's conditioning on the X, the data, and it has all the penalty terms in there that depend on the prior, not just on the likelihood. So that was critical to get the prior in there. At the bottom of the slide is the stochastic the SDE, the stochastic differential equation we analyzed. As you can see, there's some gradients in there that makes it into a Langevin algorithm, but it has the prior as well, and this is appropriate then for Langevin sampling in the Thomson sampling story. So here's our Thomson sampling algorithm, and again, we can analyze this now using all the machinery we've talked about so far. And here's the theorem at the very bottom of the page that this Thomson sampling now has a provable regret bound, and that regret bound is less than or equal to logarithm of t. This has a logarithmic, which is an optimal regret bound when we use Langevin. Okay, and I'm gonna maybe just briefly mention empirical results here. Why is Thomson sampling still so important? People use it a lot in real life. It's probably more widely used than the frequentist techniques in real industrial applications of, A/B sampling. And the reason is because you often have a lot of prior knowledge. And so this slide here, we show that if you have good prior knowledge, on the left over there, your Thomson sampling knowledge are really good. Those are the curves at the bottom. The frequentist UCB algorithm is really bad here, has high regret. It's the blue curve up above. All right. If you, on the other hand, use a non-informative prior, you still do better with Thompson sampling. That's the middle plot there, okay? So you don't have to have the right prior, just an okay prior. If you use exactly the wrong prior, that's the right plot over there, you do a little worse now with the Thompson sampling than the UCB, but hardly worse, not much worse. So it's a robust algorithm. Okay, so I'm going to finish there. Thanks for being patient with me. Just to kind of go up to the highest possible level here, this talk is kind of the first part of a second talk where I get into market mechanisms and decision-oriented machine learning. I think that our era has focused, with great utility on pattern recognition. So neural nets and all of our Bayesian machinery are basically doing regressions and classifications and trying to find patterns in data that are useful, for inferential and predictive purposes. And I think that's great, but lots of real-world applications demand that you actually help with decision-making. You do it quickly, but you do it safely. You have uncertainty taken into account. You have multiple decisions, and so on and so forth. So you need to have a whole kind of new field emerge that's really kind of David Blackwell-style thinking, re-emerging to tackle the decision-oriented side, including things like market mechanisms and simultaneous decisions and so on. And so I mentioned that in the context of this talk, because that kind of work is also dynamical systems oriented. It's also algorithmic. It also demands optimization and MCMC kind of machinery to be able to do those kind of things algorithmically as well. All right, so I'm gonna, with that, finish, and I'd be more than happy to answer questions if there are any, if there's time. Thank you.
Right. Well, thank you very much, Michael, for such an interesting talk. And in fact, there are lots of questions here in the question and answer panel. And so I'll just be, follow the majority and read off the questions that are having the highest upvotes. So Matthias is actually interested in the following. Information geometry is another way to look at geometry for probability distributions and gives rise to natural gradients and so on. How is this, however, this view is static, there's no optimization. Is there any relation to the geometries and dynamics that you are considering?
I'm going to say something that's a little negative, and I shouldn't, but I don't think information geometry goes very far. It's really not a dynamical system story at all. It's not an algorithmic story. It really is a way to think about the exponential family of probability distributions. It's just kind of a geometric picture on the exponential family. And I know how to think about the exponential family in other ways. I don't really need the geometry there. So I don't think the geometry turned out to be that helpul there. Here it's critical because it's all about the flow. It's all about the dynamics. It's all about the speed. It's all about, the non-exponential family distributions we can handle and so on and so forth. So I'd say the tools here, go far beyond the kind of fairly narrow use of differential geometry that you see in information geometries. That was probably overly provocative, but that's just my opinion.
All right. So then Adria asked the question, what is the reason that the discretized accelerated descent system becomes unstable when the clock is too fast? Is that true for any constant step size?
Yeah, it is. And the reason is basically that the optimal path, the speediest path, has too high of a curvature. And you don't know you're at that point of curvature until it's too late with the gradient method. And so you overshoot and you get out of the range in which there's kind of a stable pull, pulling back towards the curve. So you've trying to speed with your sports car along the curve too fast, and it just cannot be done. So now if you slow down the step size, then you will slow down the convergence rate, and that's not what you want to do.
Mm-hmm. All right. I think there were a couple of technical questions that are all similar. So could you talk a little bit more where the general bregman Lagrangian is coming from?
Okay, that's a great question. Thanks for asking it. There's not a great answer to that question. We reverse engineered all the existing accelerator algorithms we knew, and we found a thing which captured them. And that's what often happens when you do Lyapunov kind of things and Lagrangian things. You reverse engineer. And I'm pretty sure that's like what Lagrange originally did when he, took F equals ma and wrote down an action. But after about 100 years in physics, it was discovered there were underlying symmetry principles that gave rise to Lagrangians and Hamiltonians, right? Noether and so on, and Hamilton. And so they were thinking at a whole nother level of abstraction, and we don't have that here. We don't have that level of abstraction. We do not know, we don't have a theory for why the Bregman Lagrangian is the right Lagrangian. We don't have symmetry principles, if you will, or things that we should be conserving and all that. So I think there's a whole other layer of understanding. Ideally, yes, I'd be able to tell you, here's some axioms. And from those axioms, I get this Bregman Hamiltonian. And from that, I get everything I told you in the talk. But I don't know what that is yet. And it's an open problem about how to kind of figure out, I use the word symmetries. That's the only word I know how to use here, but we don't know what those symmetries would be. In fact, this Bregman Hamiltonian has unknown symmetries. We don't know what they are. It doesn't have the classical symmetries of classical mechanics. So even discovering what they are might be revealing.
Mm-hmm. All right. There are more questions coming up as we speak. So Matthias again has another question. Can your analysis also be used in the setting of stochastic gradients? And maybe adding my own question also, would the variational principle be similar for sampling algorithms compared to optimization problems? So maybe they can be.
Okay, those are two different but really great questions. First of all, yes, we do a lot of work on stochastics. Our latest paper with Chi Jen, the one I kind of advertised, it's coming out of the JACM, extends all of the work on saddle point avoidance to stochastic case. So yes, very much so. Stochastic gradient descent is a special kind of stochastics, right? It's a kind of axis parallel stochastics. It takes a data set and then it takes a subsample of that and it moves in the direction defined by that subsample, right? So in some ways, that's not a particularly good way to do things from a mathematical point of view. You'd like to kind of be able to go in a ball. So the mathematics became a little more challenging there, but we were able to definitely do that. And then there's a lot of work that relates Langevin to SGD. We've done some of that, but others have too. Now, to your question about, is there an underlying variational point of view on all the stochastic stuff? And the answer is really no. We don't really have that. There is, and it's now partly my own ignorance. There's areas of mathematics, potential theory and Malevin calculus, which kind of talk about, they advertise themselves as we're the calculus variations for stochastic systems. So presumably they would have the tools that would allow you to write down something like a Bregman Lagrangian for, deriving SDEs. But I don't know enough about that kind of mathematics to know how to do that. And I'm not even sure it's actually done. I think of the people who did all the SDE work, Brownian motion and all, it was like physics people and finance people. And they were interested in using it as a modeling tool. They were not using it as an optimization tool. So they were just happy to write down a Brownian motion and show it converged. And they weren't trying to ask the variational question of, is there an optimal way to converge, right? They're not trying to say that Brownian is optimal anyway, it's a phenomenon. And so if you're trying to say, what's the fastest way to diffuse down the hill? That's a variational question. I don't know what the answer to that is. I don't even know how to formulate it, but it's another open topic and it probably exists as an area of mathematics. I just don't know about it, but a really great question.
All right. So maybe to kind of wrap up the session with the last question, somebody asked, can we get the slides? Or can you point us to?
I can provide them easily, happily. But Stefan, that's up to you to figure out how to do that.
Great. Okay, we'll make sure to publish them on the website if that's okay. Good. I think that's probably a good duration for question and answer session. So thank you again very much, Michael, and thanks everyone else for making that possible. And I look forward to the next session then next week. Right.